Hello, geometry students. In our last lesson, we learned all of the vocabulary of circles. So in this lesson, this will be day one of learning how to find different measurements of arcs and chords and angles and all those things that we defined in our last lesson. So let's start with a central angle. Remember from our last lesson, we defined a central angle as an angle whose vertex is at the center of the circle, and we will measure that angle like we measure all angles in degrees. So the measure of this angle is called B. The measure of angle B is x degrees, and I just want you to make a note that the measure of x, the measure of a central angle, will always fall between 0 and 180 degrees. Obviously, it has to be bigger than 0, and once you get to 180 degrees, then you're not talking about a central angle anymore. You'd be looking at a semicircle. The next thing I want you to make note of is in this picture we have central angles 1, 2, and 3 that would take up the entire circle. So I just want you to know that the measure of all of those central angles, the measure of angle 1 plus the measure of angle 2 plus the measure of angle 3, would total 360 total degrees. Okay? In the next picture, notice we have two central angles here. We have angle 1 and angle 2, and those two angles intercept arcs of the circle. Well, what if those two angles were congruent? If angle 1 were congruent to angle 2, let's go ahead and mark that. Then notice that can tell us something about the associated arcs with those angles. If angle 1 is congruent to angle 2, then we can conclude that the arcs that they intercept are also congruent. So that means arc FG would be congruent to arc JH. All right, so let's go ahead and mark that, okay? And I want you to know that also the converse is true. If we have two arcs of a circle congruent, then we can conclude that the central angles that intercept those arcs are also congruent. So let's go ahead and make this arrow a two-way arrow. Okay, so this is biconditional. If two central angles are congruent, then the arcs that they intercept are congruent. And conversely, if two arcs of a circle are congruent, then the central angles that intercept those arcs are also congruent. Next, we're going to talk about the arc addition postulate. Now, this sounds familiar to you because already this year we've studied a segment addition postulate and an angle addition postulate. So the arc addition postulate would be very similar to that. What we're going to do is we're going to look at arc XY and arc YZ, and the arc addition postulate is going to tell us that the measure of arc XY plus the measure of arc YZ is the same as the entire measure of arc XZ. So let's write that down. We would say that the measure of arc XY plus the measure of arc YZ is equal to the entire arc, the measure of arc XZ. Okay? And the next thing we're going to talk about is arc length. So take a look at this arc, and we're going to call its length L. And I want you to think about what kind of a number that would be. If you could take a piece of string and lay it along the part of the circle and then stretch that string out straight and measure it with a standard rule, either an English rule or a metric ruler, then you'd have a number of inches or a number of centimeters or feet or meters or something like that. So arc length is the actual length of the arc if you were to stretch it out and to measure it. So there's a formula for finding arc length. We find arc length by taking, now the length of this arc would be a portion of the entire circumference. And the way we figure out the portion is by using this central angle that intercepts that arc. So what we're going to do is put x, the measure of that central angle, over 360. So x 3/60 times the circumference of the circle would give us a portion of the center of the circle. Okay, so a portion of the circumference of the circle. So to find the length of an arc, we will take x 3/60, just put it over 360 and multiply it by the circumference. So for example, if x were 90 degrees, then 90 3/60 would be a fourth. So L would be the fourth of the circumference of the circle. If x were 30 degrees, then 30 3/60 is 1/12. Then L would be 1/12 of the circumference of the whole circle. Okay, so that's arc length. Now the next thing I want you to see is arc length using radians. Okay, now radian is a unit of measure that we haven't studied yet this year. You will see it again when you study pre-calculus, but a radian is a different way to measure an angle. In Euclidean geometry, we've been measuring angles using the unit of degrees. So a radian is a different unit of measure. You will study this a lot more in depth when you get into pre-calculus. But just for now, all you need to know is that a radian is a different unit of measure for measuring an angle. So we can find arc length the traditional way, or we can also find arc length using radians. So to find arc length using radians, again, that arc length is L, we would just take, not L equals, we're going to use the measure of the central angle, which, as you can see, is theta. So it would be theta equals L, the arc length, divided by the radius. Okay, so you'll have some problems in your homework where you will be asked to find arc length using radians. You will be given theta, the measure of the central angle. You'll be given r, which is the radius, and then you can do the algebra to find out what arc length is. Okay, in this next picture, you'll see the two chords in a circle. Let's assume that those two chords were congruent. All right, so let's assume that segment FG, chord FG, is congruent to chord JH. Okay, well, you'll notice that the two chords intercept two arcs. So the conclusion is going to be that if those two chords are congruent, then the arcs that they intercept, that would be arc FJ and arc JH, those two chords are congruent as well. So if two chords of a circle are congruent, then the arcs that they intercept are also congruent. Okay, and the converse is also true. If we have two chords of a triangle, this isn't a triangle, sorry, and they're not chords either. Let me start that whole sentence over. If we have two arcs of a circle that are congruent, then their corresponding chords will also be congruent. So let's make this arrow a two-way arrow. This is biconditional. If two chords of a triangle, two chords of a circle are congruent, then their corresponding arcs are congruent, and conversely, if two arcs of a circle are congruent, then their corresponding chords will also be congruent. Okay? In the next picture, I want you to notice that we have a diagonal AB, that is perpendicular to a chord. So that's going to be the hypothesis of our theorem. Segment AB, which is a diagonal, is perpendicular to segment XY, which is a chord of a circle. Okay, so when we have a diameter, or we could also extend this to say if we have a radius, segment CB is a radius, segment AB is a diameter. So if we have a diameter or a radius that is perpendicular to a chord, then two things are going to happen. Okay, our conclusions are, number one, that the chord is going to be bisected. Okay, so if a diameter is perpendicular to a chord, then it's going to bisect that chord. In other words, segment XZ would be congruent to segment ZY. Okay, the chord is being bisected. And also, notice that there is an arc that is associated with that chord. Okay, if a radius or a diameter is perpendicular to a chord, not only does it bisect the chord, but it's also going to bisect the arc. So in other words, we can also conclude that arc XB is congruent to arc BY. This next diagram represents the converse of the theorem in the previous diagram. Here we have a segment AB that happens to be the perpendicular bisector of a chord. So that's the hypothesis of our theorem. We have a segment AB that is the perpendicular bisector of a chord, and that chord is chord XY. Well, if that's the case, if we have a segment that bisects a chord and is perpendicular to a chord, then we can conclude that that segment has to be a diameter. So our conclusion then would be is that segment AB is a diameter of the circle, It's the diameter of circle C. And we could also say that segment CB, which segment CB would be the radius. Okay, remember a radius is half of a diagonal. So if we have a segment that bisects a chord, that segment and is perpendicular to that chord, then that segment must be a diameter, which means CB would also be a radius. In this next diagram, I want you to notice that segment PX is perpendicular to FG and segment PY is perpendicular to JH. Well, if PX and PY are perpendicular to these segments, that means that the measure of then PX is representing the distance from P to FG, and PY is representing the distance from P to JH. Remember, the shortest distance from a point to a line is the measure of the segment that's perpendicular to a line. So we have, in this diagram, we have a couple of chords, and we have the distances from the center to the chords represented. So suppose in this diagram the two chords were congruent. Well, if the two chords were congruent, if segment FG is congruent to segment JH, then we can conclude that those two chords are equidistant from the center. If these two chords are congruent, then they are equidistant from the center. So the way that we would say that is we would say measure PX. Notice I'm not putting a bar over that. So that's the distance from P to X is equal to the distance from P to Y. Okay? So if two chords are congruent, then they are equidistant from the center. Now the converse is also true. If two chords are equidistant from the center, then that means those two chords are congruent. So we can take this arrow and we can make it a biconditional arrow because this is a biconditional statement. If two chords are congruent, they're equidistant from center, and conversely, if two chords are equidistant from center, then those two chords are congruent. In the next diagram, you'll see a picture of an inscribed angle. Remember, an inscribed angle is an angle whose vertex is on the circle and whose sides are chords of the circle. So in the last lesson, you learned what an inscribed angle is. In this lesson, we're going to learn how to find the measure of an inscribed angle. So the measure of an inscribed angle has something to do with this arc, the arc that it intercepts, and it's not going to be equal to the arc that it intercepts. Remember, the measure of a central angle, let me draw this central angle. Remember, the measure of a central angle is equal to the arc that it intercepts. You'll notice that the measure of angle 1 is much smaller than this x degrees, and as it turns out, the measure of angle 1 turns out to be half of x degrees. So whenever you have an inscribed angle, an angle whose vertex is on the circle and whose sides are chords of the circle, then the measure of that angle is always going to be equal to 1/2 the measure of the arc that it intercepts. Okay? In this next diagram, I want you to notice that we have angle B and angle C that intercept the same arc. Okay, so angle B intercepts arc AD and angle C intercepts arc AD. So it makes sense. These are both inscribed angles. Both of them would be equal to 1/2 the measure of the arc that they intercept. Well, since they intercept the same arc, I think we can easily conclude then that those two angles are congruent. Okay, so let's write out that theorem. If angle B and angle C intercept the same arc, and that arc is arc AD, okay, then we can conclude that those two angles are congruent. Angle B is congruent to angle C. In this next diagram, let's take a look at angle G. Angle G is another inscribed angle, but I want you to notice that since FH passes through the center, FH is a diameter, which means FJH is a semicircle. I'm going to highlight that semicircle. So here's the semicircle. So what we have is we have an inscribed angle that is intercepting a semicircle. Well, since we've already learned that the measure of an inscribed angle is equal to 1/2 the measure of intercepted arc, that means that angle G is 1/2 of 180 degrees, which means it's 90 degrees, which means it is a it's a right angle. So let's state our theorem like this. If angle G intercepts semicircle, which the name of that semicircle would be arc FJH. Remember, you name semicircles and major arcs with 3 points, okay? So if angle G intercepts a semicircle, then we can conclude that angle G is a right angle because it's intercepting a 180-degree arc, and a half of 180 degrees is 90 degrees. Last but not least, let's take a look at what happens when a quadrilateral is inscribed in a circle. Remember, a polygon is inscribed in a circle if all of its vertices lie on the circle. By the way, so we would say quadrilateral KLMN is inscribed in circle A, or we could say that circle A is circumscribed about quadrilateral KLMN. Okay, so our hypothesis then is that we have a quadrilateral, KLMN that is inscribed in circle A, okay? Well, if that's the case, then what we're going to be able to conclude is that its opposite angles are supplementary. Angle L and angle N are going to be supplementary, and angle K and angle M are going to be supplementary. So let's list that. Angle L and angle K, angle K, no, I'm sorry, it's not K, it's N. Angle L and angle N, a pair of opposite angles, are supplementary, and likewise, angle K and angle M, not ammed, let me spell that right, sorry. Mercy, I'm having trouble. Okay, angle K and angle M are also supplementary. All right, so whenever a quadrilateral is inscribed inside of a circle, remember its opposite angles are going to be supplementary. In other words, their measures add up to 180. Okay, you might want to keep these notes handy as you go to do your worksheet, and if you have any questions, be sure and let me know.